Okay, let's look at a theorem that's of fundamental importance. I might even go so far as to call it a fundamental limit law. So we want to suppose that two functions are equal everywhere except possibly at a single point x equals c. And we'll look at an example of what this looks like in a minute. So the limit as x approaches c of f exists if and only if the limit as x approaches c of g also exists. And in this case, when they both exist, the two limits must be equal. So we saw in an example, like if you can't plug in the number, right? If you've got some function that you can't plug in the number, maybe you can rewrite it in such a way that you can plug in the number. So that's how we're going to use this thing. Before we look at examples of limits, let's look at what it means for two functions to be equal everywhere except at a single point. Okay, here's an example of two functions that are equal everywhere except at a single point. And we can see what that single point is. So here's a function f, and it's 2x minus 2 over x minus 1. And of course, you can factor out a 2 and write this thing as 2 times x minus 1 over x minus 1. And you could then cancel the x minus 1s, and you'd be left with 2. But to say that the function f is equal to 2 is incorrect. In fact, here's a function g of x that's equal to 2, right? This thing is equal to 2 everywhere. This thing is equal to 2 everywhere except at the point x equals 1. So to say that f of x is equal to 2, or to say that f of x is equal to g of x everywhere is false. In this case, we've got that f of x is equal to g of x for all numbers x except at x equals 1. Right, so here at x equals 1, the function is not defined. Here at x equals 1, the function is defined and it's equal to 2. So these two functions are equal everywhere, and we must include the condition that x is not equal to 1. So f of x is equal to g of x everywhere except at x equals 1. Here's what that looks like, right? Maybe a deleted point. Maybe we define the point down here somewhere. Either way, these two functions are not equal unless I fill in the deleted point, which I'm not allowed to do, right? Because 1's not in the domain of this thing. Okay, now let's look at an example of how to apply that previous limit theorem, fundamental limit law. Here's the example that we just looked at. So we want the limit as x approaches 1 of 2x minus 2 over x minus 1. So again, it'd be nice if we could just plug in the number, but we can't. So we need to try to rewrite this function in such a way that we can plug in the number. So we want to use that fundamental limit law. So here's how I'm going to use that. We know that 2x minus 2 over x minus 1 is the same thing as 2 times the quantity x minus 1 over x minus 1. And now I'm allowed to cancel the x minus 1s, and I'm left with the function 2. Again, this thing is not equal to this thing. We need to add a little condition, namely that x is not equal to 1. So now we know that the left-hand side is equal to the right-hand side. So this is my f of x, this is my g of x. These two things are equal everywhere except possibly at x equals 1. That means they will have equal limits at x equals 1. So by the fundamental limit law, this tells me that the limit as x approaches 1 of 2x minus 2 over x minus 1 is equal to the limit as x approaches 1 of the function 2. And we know how to evaluate that. That's just, it's a constant, so the answer is just 2. So that would be a good final answer to this thing. Here's an example. We want to evaluate this limit. Again, you try to plug in the number, try to plug in 2 everywhere you see an x, and you get a thing of the form 0 over 0. We will call this an indeterminate form. That limit may or may not exist. 0 over 0 suggests that we may have a shot at rewriting the function in such a way that we can just plug in the number after we rewrite it. So how do you deal with this? So you see that the problem factor here is x minus 2, so we'd like to cancel that out if possible. So let me just start with the function x squared minus 4 over x minus 2. That's the same thing as x minus 2 times x plus 2 over x minus 2. And now I'm allowed to cancel these two things. And so I'm left with x plus 2. But if I stop now, what I have on the board is false. It's incorrect. These two functions are not equal. They are equal everywhere except at x equals 2. So we need to throw in x not equal to 2. So now you've got this left-hand function, call it f, and you've got this right-hand function, call it g of x. These two things, f and g, are equal everywhere except at x equals 2. That means they have equal limits at 2. So now I know the limit as x approaches 2 of my original function. It's equal to the limit as x approaches 2 of the function x plus 2. Much easier. Now this thing, we can plug in the number, right? This is a polynomial, and we know that to evaluate the limit of a polynomial, you just plug in the number. So here I'm just going to get 2 plus 2, so here I get a 4. So 4 would be a good final answer, together with showing all of this work for this limit. Here's another example. Again, this looks like one of the functions from the basic library or an elementary function. Problem is that we can't plug 0 into this function. 0 is not in the domain of this function, so that plug in the number theorem is not going to apply here. Here's what does happen. If I plug in 0 everywhere I see an x, I get a thing of the form 0 over 0. Again, we will call that an indeterminate form. We may or may not be able to rewrite this function in such a way that does allow us to plug in 0 at the end of that process. So if you get a square root and you need to rewrite the thing, you might want to try the old conjugate trick from high school. So I'm going to multiply the top and the bottom by the square root plus 3, right? That's the conjugate of this expression. So here I'm going to get square root x squared plus 9 minus 3 over x squared. And I'm just going to multiply the top and the bottom by x squared plus 9 plus 3. And then again, x squared plus 9 plus 3. So I just switch the minus to a plus, and that's how I get the conjugate. Now, we have a thing of the form a minus b times a plus b. And I know when I multiply those two things together, I get a squared minus b squared, right? That's just the difference of two squares. So a squared just says the radical squared, so take away the radical. And then b squared, well, that's 3 squared, which is 9. So here I'm going to get x squared plus 9 minus 9 in the numerator. And then in the denominator, I get x squared times the conjugate, whatever that is. And so now what's going to happen? So the 9's will cancel. And now I'm left with x squared over x squared times a thing. So the x squareds will cancel. And now I'm left with 1 over the thing in the parentheses. So square root x squared plus 9 plus 3. This is not the whole story. This function is not equal to this function. It is, though, everywhere except at x equals 0. So this is true, right? this thing is equal to this thing everywhere except at x equals 0. So now we can apply the fundamental limit law. That tells me that the limit as x approaches 0 of this thing is the same thing as the limit as x approaches 0 of 1 over square root x squared plus 9 plus 3. And notice we have gotten rid of the troublesome factor x squared, right? So now I can plug in a 0 everywhere I see an x. And when I do, I just get 1 over 6. Right? Plug in a 0 where you see an x, a square root of 9 is 3, 3 plus 3 is 6. So at the end of the day, a good final answer for this limit using that fundamental limit law together with the other basic limit laws, I just get that this thing is equal to 1 over 6. That would be a good final answer.